Hello everyone. Today inshallah I will continue solving on the topics that we already did go through in the previous lecture. Please try to go through it. You will find I usually feel more comfortable about sharing the PDFs from Lisbon on the WhatsApp. Also you will find them downloaded on Moodle, but I usually send you the Lisbon slides on WhatsApp plus the PDF for my slides, which cover both the homeworks, the exercises, and the Lisbon slides also. Okay. And of course you have the recorded lectures on the YouTube. I will start, although we took the directed derivative in the previous session, but I would like to refresh your information about it. As I was telling you before we start recording, and in the introduction, in multivariable calculus, Omar, what's the multivariable calculus? It is the case of Rn into R. It is the case of handling more than two variables. The directional derivative generalizes the idea of a derivative to functions of several variables. Instead of measuring the rate of change in just the x and y directions, and you will see that the xy directions are just special cases from the directional derivative. You will see this in the coming slides. Okay? It tells us how a function changes in any given direction. This is the importance of the directional derivative. The second paragraph states that if you have f, x, or y, a function, and let u be a unit vector, Hussein, how to get a unit vector? If I have, yes, you are right, if I have any vector, I can put it into normalization, Ya Omar, or make it a unit vector simply by dividing the components of this vector on its norm. What's the norm, Adam? The norm, it is the square root of the squares of the components. So any vector, I can change it, as you will see, as a unit vector, Mr. Hussein. Okay, of course, once it is a unit vector from its name, so the length is going to be equal to 1. Representing a direction, the directional derivative of f at certain point in the direction of u measures how fast f changes as we move from x node, y node in the direction of the vector given. The directional derivative is given by this definition. Omar, please look at this definition carefully. It is the limit of t tends to 0 for the function which is at x node and y node. I will add t times u1 plus t times u2, those the input inside f, minus ziyad f of x node, y node, divided by t. If you remark, that's the function that's given. This is f of xy. All I have to do, Adham, is to substitute at the point that I am getting the direction vector at it. So I will replace x and y by x node and y node. Then, in order to get f, all I have to do is to put x node, y node, but plus t times u1 and u2. Omar will ask me, what is u1 and what's u2? They are the components of this vector. That vector, okay? So simply, if you look to u1 and u2, those are the components. Muhammad, I will use this equation or this limit or this expression if the function is not differentiable, or if the function is a piecewise function. I would feel more comfortable finding the directional derivative using this one. But if the function is continuous and differentiable, Mr. Hussein, instead of the previous form, I can use simply the gradient vector form, which is much easier. It is the gradient of the function, we know how to get the gradient vector, times or dot u, which is the dot product in u, okay? And we will see problems on this. Of course, you know that the gradient vector of f is simply partial f, partial x, partial f, partial y, which means you will differentiate the function with respect to its variables. Of course, I will substitute in the gradient vector by the point at which I'm evaluating the directed derivative, as we did in the previous session. Remark that if the directed derivative of the function is greater than 0, means the function is increasing in this direction. And if the directed derivative of the function is less than 0 as a value, it means the function is decreasing in this direction. And if it's equal to 0, so there is no change. Important, those are the two special cases, Muhammad, that I told you about. The partial derivative in the x direction, it's a special case from the directed derivative. Look, if u is 1 and 0, that's the unit vector in the x direction. So if I multiply this guy by the gradient vector, so multiplying the gradient vector by 1 and 0 will make just only the first component to appear, which is gonna be the partial derivative of f with respect to x. Same way, like if I am getting, okay, look at this. If I'm getting the derivative, okay, look, if I'm getting the directed derivative, the directed derivative of f in the direction of 0 and 1, this is gonna be the gradient vector of f, which is simply partial f partial x, partial f partial y, dot the vector, which is 0 and 1. Of course, the dot product means you will multiply the first components in each other. Multiply كده زياد. It's gonna be partial f partial x times 0, which is gonna disappear. And you will have partial f partial y. So once more, if I am getting the directed derivative in the direction of 0, 1, then it's gonna be the partial derivative with respect to y, which stress or confirm that I can get the partial derivative of a function in any direction based on the direction of the vector, but it has to be a unit vector as you saw. Of course, this is a unit vector because simply if you get the magnitude, Muhammad, can you get the magnitude of u or the norm of u? It's very, very simple. That's the norm of u, which is the square root of the first component to the power of 2 and the second component to the power of 2, which is going to be root of 1 square, which is equal to positive 1. Okay? So that's the unit vector in this direction. Okay, Shabab? This is a special case from this problem. Once more, an example on the steps that I told you about. I need to solve this problem. The one who's going to solve this problem with me is Mr. Omar. Omar, wake up كده. Let's try to solve this problem together. Okay. Read. Find the directional derivative of 1 and 1 in the direction of v. I need three things. معايا Mr. Ziad, I need three things. The function, the vector, the point. I have them. This is the function that I have, and that's the vector that I need to find the directed derivative in its direction, and this is the point. Before we start, I will need to decide, Mr. Hussein, am I going to use the gradient vector formula or the limit formula? How to decide? This is just only a polynomial function, am I right? Okay, so it is differentiable, صح? So simply, I will do 3 steps. I will solve it with you step by step, then we will see the slides, how it is written. The first thing to do is to, I'm very comfortable. Now I know that if I want to get the directed derivative of the function f at the point, which is the derivative at 1 and 1, in the direction of the vector v, this is gonna equal to the gradient vector of f dot the vector v, but it has to be a unit vector. In order to do this, I will go through the steps one by one. The first step is to normalize the vector. The vector is gonna equal to, this is the norm of v, which is the square root of the first component to the power of 2 plus the second component to the power of 2, which simply is a root 5. Is this equal to 1? It's not equal to 1. معايا عمر? So it's not a unit vector. How to be sure that this vector is a unit vector? I will divide Mr. Ziad the components of the vector on its norm. So my vector at this time will be simply the first component, which is 1 by root of 5, and the second component, which is 2 over root 5. This is how to normalize the vector. So instead of dealing with 1 and 2, I'm dealing now, Mr. Adham, with 1 over root 5 and 2 over root 5. And that's a unit vector. That's the first step. The second step, I will get, Mr. Hussein, the gradient vector. Let's get the gradient vector of f, which is simply f sub x and f sub y. F sub x means you will differentiate this function with respect to x. Let's differentiate with respect to x. Differentiate. So it's gonna be just only 2 of x. This is 0. Differentiate with respect to y. So the first component, 0. The second component is 2y. Really very simple. Now get the gradient vector of f at the point, which is 1 and 1. So all I have to do is to start substituting, which is gonna give you 2 and 2. Any problem? The final step, Ya Omar, I will try to substitute in my equation. So the directed derivative of this function at the point 1 and 1 in the direction of the vector, which is 1 over root 5, 2 over root 5, is gonna equal to multiply the vector times the gradient vector. The gradient vector is 2 and 2 times the vector, which is 1 over root 5 and 2 over root 5. Multiply them together, so it's going to be 1 over root 5 plus 4 over root 5, which is going to be 5 over root 5, or simply root 5. That's the value of the directed derivative at 1 and 1 in the direction of the vector given. As you can see, it's the steps are delivering one to each other. So it's really very simple to deal with it. Let's do it once more on the slides. So once more, Yalla. The first step, I will try to check, as I told you, the vector. فعلا, it is the square root of the first component to the power of 2, the second component to the power of 2. The sum is equal to 5, so normalizing is going to be 1 over root 5 and 2 over root 5. The next step is to find the gradient vector, as we did together, saying it's 2x and 2y. Substitute at 1 and 1, it's 2 and 2. The third step is to start multiplying both of them together. That's the value of the gradient vector times the vector that I have, so it's a 6 over, multiplying of course 2 times 1, it's 2 over root 5, 2 over times 2, which is 4 over 5, adding them together, so it's a 6 over root 5, as you can see. It seems like I missed the addition in the previous solution. As you can see, it's really very simple. Okay, remark that to compare directional derivatives, if I have the function that have multiple directional derivatives, it is useful that they use vectors with the same norm. This is why we are normalizing the vectors, using them as a unit vector. This is the reason. I can find the directional derivative in the direction of any vector, but in this case it will depend on the length of the vector, so comparing them is not going to be an easy task. That's another problem. I want you to calculate the directional derivative of f along the vector 1 and 2 at the points 3 and 0. Ziad, can you solve it? Yes. Okay. The same steps as we did previously. Of course, the function is differentiable because it's a polynomial function. So it's going to be easy on me to get the gradient vector. Okay, so the gradient vector, can you give me the gradient vector for this function?
Help me.
Huh?
Help me.
A?
Help me.
That's the gradient vector of f. Yes? I will differentiate with respect to x. The derivative with respect to x will be 2y cubed.
Yes.
The derivative with respect to y will be 6 x y squared plus 4. That's the derivative of the function with respect to x and with respect to
بلس 4
y.
واي بقى.
ايه؟
بلس 4 واي.
لا مش انت لما differentiate with respect to y it's gonna be 1.
with respect to y.
يبقى 1 times 4 ولما differentiate with respect to y, this is y cubed, so it's gonna be 3y squared, and of course 3 times 2 it's a 6xy squared. Okay. The second step, okay, I need to check if the vector is a unit vector. If the vector is a unit vector, this is the vector, which is 1 and 2. How to check? Get the norm. How to get the norm? So the norm of V is simply the square root for the first component to the power of 2, the second component to the power of 2, which is root 5. Since this number is not equal to 1, it's not a normal, it's not a unit vector. How to change it to be a unit vector? I will divide the components of the vector on this magnitude. So my new vector V, which is a unit vector, simply can be, I will divide 1 over this value, then 2 over root 5. Now I'm almost done. Okay, I need to find the gradient vector at the point. So I will start substituting by 3 and 0 in the gradient vector. How it's gonna be? Substitute. That's the gradient vector of f at the point 3 and 0. If I'm substituting, so I will replace y with 0, so the first component is equal to 0. Then I will replace y with 0, this is gonna be 0, so it's gonna be 0 and 4. Now I can find the directional derivative, or the directed derivative, which is simply gonna be the dot product of 0 and 4 dot this value. So once more, this is the first step that we are going to have, differentiating with respect to x, differentiating with respect to y. As you can see, this is 2y cubed, 6xy squared plus 4, exactly as we did. The second step is trying to find the gradient vector at 3 and 0. So I'm going to substitute in this coordinates by 3 and 0. That's the result, which is 0 and 4. Now checking the vector. This is the vector 1 and 2. The norm is root 5. How to change it to be normal vector? I will divide the components on the magnitude. So it's going to be 1 over root 5, 2 over root 5. Finally, I will multiply them together. As you can see, finally, I can get the directed derivative by multiplying 0 and 4 times 1 over root 5, 2 over root 5. So the first component is going to equal to 0. The second is going to be 8 over root 5, as you can see. It's really very simple, but I'm telling you, if you didn't try to solve it using your pen and paper and writing all of this, it's gonna be confusing down the road. Next, here is the normalized, another problem for normalizing directional derivative for x squared y squared, and this is at 2 and 1, that's the point, and that's the vector. One of the common mistakes that usually people do, they mix what's the vector and what's the point, so they replace them instead of each other, and that's a common mistake. So please be careful about this. The first step, as I told you, getting the gradient vector. The next step is to substitute in the gradient. This is the value at the indicated point. Checking the normal vector. Okay, I have V as a unit vector. Then finally, I will multiply them together, multiplying 4 and 2 times this value of our vector. As you remark, the value is greater than 0. Once it's greater than 0, Hussein, it means it's positive, which means the function is in the direction of increasing at the direction of this vector. That's another problem with the similar steps, exactly the same. So getting the gradient vector, the values, the multiplying once more. As I told you, I've tried to put plenty of problems with the same sequence 1, 2, 3 in order to make it easy for you to digest this part. Now I want to identify the maximum directed, or the direction of maximum growth. The direction of maximum growth is really very simple. It is when the vector is equal to the gradient vector. So once you find the gradient vector, use this gradient vector to be the vector that you are studying, the directed derivative in its direction. So once more, look, If f is differentiable at A, then of all vector with norm 1, the one which implies the greatest directional derivative at A is the unit vector associated to the gradient vector evaluated at that point. لذلك, so, boss Mr. Hussein, that's the vector. Look to the vector that I'm using. I'm using the gradient vector. So I'm getting the directed derivative, but in the direction of the gradient vector. This how you will get the maximum direction or the value of maximum increase or maximum growth. So for this problem, he wants you to define, he is giving you a function which is 3 times e to the power of xy minus 1 plus x times ln 1. That's my function. Of course, it is differentiable and well behaved because as you can see, this is an exponential function and the other is logarithmic function. The only regulation in the domain, for this one, it is working with R2. But for this part, you have a regulation. The regulation is y greater than 0. So this function as a domain, it has to be R2, but with the condition that y must be greater than 0. Okay? So I'm working with half the plan in this case. He's asking you to show that is 1 and 1 belongs to the interior of this region, and this is one of the questions that we already covered in the first midterm. But what we covered previously, Mr. Omar, you are not going to be asked about it directly, but they are tools and the background in the back of your mind. As you can see here, 1 and 1, Mr. Muhammad, belongs to the interior of the domain of this function. Why I am sure about this? Because simply, I know that the domain of this function is R2 and such that y is greater than 1. So I'm talking about the upper half. So once you are talking with 1 and 1, it belongs to the upper half. So it is an interior, belongs to D. He wants you to define the differentiability domain of f. Yeah, same. We already covered this in the previous lecture. It is recorded, you will have to go through it. In order to define a function to be differentiable, I will have to check. Yes, you are right. It's a limit of x and y tends to 0 and 0 for r of x and y divided by the norm of x and y. How to find the error? This value should equal to 0. So this limit should equal to 0. If you evaluate this limit and it's equal to 0, then your function is differentiable. Okay, how to evaluate the value of r? The value of r simply, this denominator is f of x and y minus, remark, f sub x, which is the partial derivative of f with respect to x, times x minus 0, minus f sub y times y minus 0. So I'm replacing r by this value. Of course, this is also minus f at 0 and 0 if I'm studying the case at the origin. So once more, how to discuss the differentiability? In order to discuss the differentiability, this is the first part. In order to discuss the differentiability, I will check, okay, just a second. If in order to check the differentiability of this function, I should check for r of x or y divided by the norm of xy and see if it is equal to 0 or not. But in this problem, I'm not going to use the limit because simply the function consists of exponential part and the logarithmic part. And both of them are differentiable within the definition of the domain, which is r squared except at y greater than 0. So it is differentiable. Now, I need to justify which are the vectors u and v in R2, okay, such that f, just a second, such that f of u v at 1 or 1 is the maximum. In order to do this part, now I know the function is differentiable and I can find the partial derivatives. Let's get first the gradient vector. So I will try to get the gradient vector of f at the indicated point. The gradient vector of f is simply partial f, partial x, partial f, partial y. All I have to do is to differentiate my function with respect to x and y. Adham, please try to help me with this. I need to find the partial derivative of this function with respect to x. So the first component, the part that's going to be differentiated, the exponential part. So it's going to be e to the power of xy minus 1 times the derivative of x is 1 times y. So it's going to be 3y to the power of exy minus 1. That's for the first component. The second component, Adam, it's x plus ln 1. So differentiating with respect to x will give you plus ln of 1. It will do exactly the same, but differentiating with respect to y, not x. Differentiate with b. Once more, this is the exponential part. So it's gonna be, this is the 3, this is e to the power of x, y minus 1. Then I will differentiate with respect to y, which is gonna be an x. Then plus, I will differentiate with y. So x is a constant. So it's gonna be an x over y. That's the gradient vector, okay, of this function. I need to find the gradient vector of this function, but at the point 1 and 1. So all I have to do now is to start substituting by 1 and 1. So the gradient vector at this time, gradient of f at 1 and 1 is gonna be, let's start substituting. So this is gonna be 1 minus 1, which is 0. E to the power of 0, 1. And y is equal to 1 times 3. So the first component is 3. The second component, if I'm trying to substitute, this is going to be 1. And for this guy, it's going to be 1 times 3. So the result is going to be a 4. That's the vector, okay? Or what's representing the gradient vector at the point 1 and 1. To find the value at the maximum increase, I will need to find the directed derivative of f at 1 and 1, but in the direction of the vector 3 and 4 as a normal vector, of course. Of course, Adham, if this normal vector, so if I'm using u equal to 3 and 4, if this is a normal vector, this is not a normal vector. How to normalize it? I will divide on the components, all the components on the norm of this vector. So, which leads to that u as a normal vector, or as a unit vector, it's gonna be 3 divided by the norm of v is simply the square root of 3 to the power of 2 plus 4 to the power of 2, which is the root of 25, which is 5. So it's gonna be 3 over 5, and this is 4 over 5. Now I have a unit vector, as you can see. Now I have the unit vector. I'm finishing everything. I will multiply the gradient vector, which is 3 and 4, times the unit vector that I have, which is 3 over 5 and 4 over 5. That's the direction of the maximum increase for in the directed direction. So once you do this, you will find 9 over 5 and then plus 16 over 5, which I believe is gonna equal to 5. These are the steps. So from these steps, it's not difficult, but you have to know what you are doing exactly in order not to lose attention while, not to lose or to get confused with this problem. So once more, I will do it with you once more. That's the gradient vector, which is gonna lead to 3 and 4. I will get the vector at 3 and 4. This is the norm, this is the norm of the vector. This is the unit vector in the maximum direction, which is gonna divide the components of the gradient vector with root 5. Then I will multiply them together as you saw in the previous problem. Okay, this is another problem in which he's giving you x to the power of 2e power y, and he wants you to determine the maximum value of the directional derivative at the point. Okay? And he wants you to indicate the unit vector that defines the direction where this maximum value occurs. In order to do this, it's a really very good question. As I told you, you may be subject to some of these questions in your next midterm. This is really very tempting question. Number one, it's simple, accessible, and show me that you understand exactly what you are doing. So the first thing to do is to find the gradient vector. I will need to find the gradient vector of this guy, which is gonna simply be differentiate with respect to x, it's gonna be 2x times e power y. Then differentiate with respect to y, it's gonna be x squared to e power y. Then start substituting by the point -1 and 0. This is what I did. So that's the vector. This is my vector. So the answer for this question indicate the unit vector that defines the direction where maximum occurs. That's the vector. Remaining to put it on normalization or normalize it. Of course, if I want to give the norm of this vector, it's gonna be the first component to the power of 2, 4, plus 1, which is 5, root 5. This is not a unit vector. In order to put it as a unit vector, and this part will be answered, so it's gonna be u, which is -2 over root 5 and 1 over root 5. That's the direction. The second step, I will need to get the value of the directed derivative. So I will multiply this value times that guy, and that's it. So once more, this is the magnitude. This is normalizing, as I told you. This last step is getting the value of the directed derivative. I will multiply them together. It's going to be 5 over root 5, as you can see. Those problems are really very important, and by this example, we ended our examples in the main slides. I want to solve with you some problems that came previously in exams. So let's see this problem, which is really very close, as I told you. He wants you, let G from R2 into R be defined by G of xy to x plus y plus the square root of x, the absolute of xy sine x. Knowing that, what's Mr. Adham? Knowing that the partial G, partial x at the origin is equal to 2. I'm giving it to you directly. And partial G, partial y at the origin is equal to 1. I want you to prove that G is differentiable at the origin. How to prove that that G is differentiable at the origin? In order to prove the differentiability, as I told you, I will have to prove that the limit of x and y tends to 0 and 0 for the remainder of x and y on the norm of x and y equal to 0. I will have to prove this limit, or to find this limit. Of course, once more, R is simply, it's gonna be f of xy minus the value of the function at the origin minus the partial derivative times x minus the partial derivative with respect to y times y. So all I have to do is to get, this is the R, or this is R of xy, the function g of xy, the value at the origin, and this is the partial derivative of g at x times x, partial g, partial y at the origin times y, divided by the norm of x and y. Let's do it together, Adam. It's very, very simple. The first part, you already have it, which is 2x and y, blah, 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 blah. Type g at 0 and 0, let's substitute in this function. So it's going to be 0 times sine 0. And those are zeros. So this part is equal to 0. So if I look to this one, it is going to be x minus partial g, partial x times 0 and 0. Partial g, partial x at 0 and 0 is equal to 2. So it's going to be -2 times x. Partial g, partial y at zeros, it's equal to 1. So it's going to be -1. So what I have at the time being, just substitution, which is going to be g of xy minus 2x minus y. Replace g by its value. which is gonna be 2x plus y, the root of the absolute of xy sine x, I will eliminate negative 2x with negative 2x, positive y with negative y, and so this is the limit that I want to evaluate. I need to prove that this limit is equal to 0. Okay, how to prove this? You have plenty of methods. I can check it by the directed method. If they are all equal to each other, I will use the Cauchy definition, the epsilon and the delta definition. Or I can change variables to R and the test also. So or use the consequence of the squeeze theory, which looks really very tempting. I can separate this function to be as two parts, ziyad, which is gonna be sine of x by itself times the root of the absolute of x y divided by the root of x squared plus y squared. And that's the limit of x and y tends to the origin, and that's the limit of x and y tends to the origin. Of course, this guy is equal to 0. So all I have to do to use or to get an advantage from the squeeze theory is to prove that this limit is bounded. And this is really very simple. Because simply, this is gonna be the square of, instead of x plus y, it's gonna be less than or equal x squared plus y squared times x squared plus y squared divided by the square root of x squared plus y squared, as you can see. These two values, okay, will show that this function can be bounded, and so 0 times anything bounded is going to equal to 0. So by the squeeze theory, the value of this function is equal to 0. Once it's equal to 0, your function is differentiable. So once more, all I have to do is to use the advantage of the squeeze theory. I will try to, that's the simplest thing to do. So I will let it to be sine x, which tends to 0. This value, which is root x, root y, exactly as I did, is going to be bounded function. And so multiplying 0 by a bounded function, the result